We're almost there. I have some, actually I should plug this in. I have some funky technology stuff planned, but it sort of depends on how quickly you work and whether we'll get there or not. So, question mark. Let's see how we go. Before we get to the final conic section, in order to make sure when we get there, rather than you get there and it's like, oh, this is cool, I want to try to understand it, I have to divert you off to the side to think about this, then you'll be able to come and understand it. I thought, let's revise this. You've met this idea before. It'll seem a bit old, a bit quaint. You're like, why are we doing this? What does this have to do with anything? Answer, when we get to this, being able to interpret this quickly and effectively will be very, very helpful to us. Okay. So here's the question I want to pose to you. Okay. Not opposed to you, I want to pose to you. You've been studying functions and relations for a long time now, like good 4 or 5 years, okay? And many of the ones that you've studied, they exist. Get ready, this is not English, but it's going to be more concise. They exist for all real values of x. That's how I read that. That upside down A, it means for all. It's an upside down A because it's A for all. X, all the x's that belong to or are elements of the real number set. So let me read it again. Many functions and relations that you studied over the last few years, they exist for all real values of x. Give me an example. Y equals x. Y equals x squared. I think I heard another one. Y equals x cubed. You could go on for a while, couldn't you? Right? But they don't all, do they? Okay. Sometimes a function or relation does not exist for all the values of x, and we have what's called, we give it a name. We say, you know, it doesn't exist there, so it has it starts with R, the word restriction. We have a domain restriction. Okay. So, okay, I'm missing something. How do I spell restriction? There we go. My spelling's strong today. Domain restrictions come up in a whole bunch of functions. Now, I could just list these out for you, but I thought it'd be a little more interesting for you. Let's see if we can do this individually. I was going to make you do it in pairs, but I think that might be too easy if you're paired up. Two brains, I think you'll be able to get all of them too quickly. I want you to individually think of how many functions and relations do you know that have domain restrictions. Now, obviously, let's have a look at these three, right? These don't have domain restrictions. But I would kind of lump all of these guys together in one family of functions. Like they're different, but they're not very different. What are they all called? Starts with a P. They're polynomials, aren't they? Come in. Come in. Come in.
I'm Chrissy's calculator.
I'll take it.
She might need it.
Thank you. So, even though this is three functions, it's not really three. They're not really different enough to warrant, oh look, I know three different kinds. They're really just one kind. Okay. So I want you to think of, on your own first, how many functions or relations are going to end up with these? Don't just give me like minor differences. See if you can think of fundamentally different kinds. See how many you can think of. I wonder how many you can come up with on your own. Some are easy, some are a bit trickier. I'll give you a few minutes, have a think. Let's do it. All right. Now, hands up if you reckon you're one of the people who has the most on their list, the most different kinds. Hands up if you're like, I've got tons. How many do you have, Ruben? 9. Wowzers. Did anyone top 9? For real? Whoa! Whoa! So much! Too much. Do you guys even lift? I mean, okay, all right, fine. Now, I'm going to wager, you correct me if I'm wrong, I'm interested because I put together my own list. I'm guessing if you had 9 or 15, I blame Dad for everything. Probably you actually have a few that look different, but fundamentally they are the same. So let's have a look. Let's see if we can compare. Okay. I think the first main kind, I'll start with the ones that you know the names. I think the first main kind are rational functions. Please tell me you know what a rational function is. What is rational, apart from sensible, coherent, what does rational mean in a mathematical context? It means a fraction, because it's about a ratio, isn't it? Okay. So, examples. What's an example? 1 on x.
7,000.
Okay. 1 on x. 1 on x plus 1. 1 on x
Plus
squared
2.
minus 1. Y equals x on x minus 1, and on and on and on and on. All of these, they're all rational functions because they all have this fraction. Okay. Now, just very quickly, it has a domain restriction. Sorry, they all have domain restrictions. How do you work them out? What's the most efficient way to find out how it's restricted? It's all about the denominator, isn't it? Like, it's this guy on the bottom that's the problem. What do you do with the denominator to find where the restrictions are? Okay, so you guys said that you let it equal to 0, right? So I guess the flip side of that, the way I would say that is, this function can't exist when the denominator is 0, right? So the denominator cannot be 0. Okay? If it's anything else, you're fine. Okay? Which is why for these, you'll get vertical asymptotes, right? There's just that one value of x, or like those two values of x, okay? Just isolated spots where the function breaks down, okay? Fine, there's my first one. Next one. Now, hopefully you guys have this, but you probably don't know the name. So, please put your hand up if you have something with a square root in it. Hands up, hands up. Okay, good, not bad, right? Now, does anyone actually know what they're called? So these are fractions, ratios, but we don't call them ratio functions or fraction functions. We actually have an adjective for these, right? Now, surd would be, because you know what, surd is also a noun, but it has an adjective, which is surdic, right? It's a terrible name. What these are really called, get this, they're called radical functions. Radical actually is the adjective for the word root, okay? Which is, by the way, rad, okay? It's the same place where we get the idea of a radius or radians, okay? It's all the same root word. Get it? Root? Anyway. So you can take this. You're so slow today. You can put anything underneath it's called a radical sign actually, because if I put something like that, it's not a square root anymore. It's a cube root or the 30th root or whatever. Okay, it's still radical. Now we said over here the denominator can't be 0. Alright? What's the rule that's going to find the restriction for these kinds of functions? This thing underneath the radical, it has to be greater than or equal to 0 is okay. 0 is alright. You can take the square root or the 30th root of 0. Okay? But it has to be within that restriction. Okay. Now, by the way, we gave this a name, right? What is that thing called? That thing underneath the square root sign? I'll give you a clue. What's this whole thing called? The whole thing. Integral. It's called an integral. What's that thing called? An integrand. Now this is a radical. Legit, the actual name, go look it up, is the radicand. That's what it's called. That's an M. That's an M. Okay, what do we say about it? It's got to be greater than or equal to 0. Right. What other kinds of functions do you have? Someone give me something that I haven't named already. Log functions. Excellent. Logarithmic functions. Okay. Now, example, right? You can pick anything you like. Here the denominator can't be 0. Here the thing underneath the radical has to be greater than or equal to 0. What about this? It's just like this, isn't it? Okay. But can you have 0? No. You can't. So it actually must be positive. Like you can't have that boundary. So, what do you call that thing? I'm just going to say that number. Honestly, I actually had a bit of trouble looking this up. I know what it's called in general terms. For all of these, when you have a function of a function, you call this inside thing the argument. Does that ring a bell? So you could call that the argument, but that doesn't have anything specific to do with logs. That's what I'm going to call that number, or that function. Okay? It must be positive. Alright, now hands up if you have a type of family of functions or relations that I haven't named yet. Hands up. Anyone? Yeah, good, good. Let's see, drive it. What did you have? Tan. Good. Okay. So, now hold on a second. Hold on a second. I think tan is already on the board, isn't it?
Yes, it is.
Which one is it? That one. It's that one. No, tan is actually an identity, isn't it? It's sine over cos. It's rational. Okay. Nice try. Let's try again. Let's try again. Give me another one. Yep. Say it again. Inverse trig. Inverse trig. Okay, hold on. Stop for a second. Does that belong in any of these? Is it rational? Who reckons it's rational? Rational implies there's some kind of fraction, right? Say something like this. Where's the fraction?
Where's the fraction?
Where's the fraction?
X equals sine y.
What the?
Where's the fraction?
10 on cos. Y.
Now this is interesting. I'm going to leave this guy off the side. Part of the problem here is inverse trig functions, as we go into them later, they follow some weird arbitrary rules. Some rules that we decide, right? For instance, these two guys are not the same, right? And most of you have not looked at this, okay? But these two lines are not equivalent. They're very close, but there's a crucial difference. The difference, though, is one that's imposed by us. It's a human, like we just define a difference, okay? So I'm going to leave him off for a minute. I'm not sure if he really fits under any of these, but okay, there are restrictions, but they're under a different category, I think. Anyone else? There's a big category that we're missing. I think I heard it. Yeah, circles. Okay, now, hold on a second. Some of you might have said, sorry, where did you think it was? Where would you put it? Okay, all right. I think we're based onto something here, right? Let's say what is a circle? I'm gonna leave this part blank for a second. Okay, give me the equation of a circle. You're so boring. Okay, so I heard an R squared, but all right, there's the unit circle. Fine. Okay. Now, I think there's some logic here in saying that this is kind of close to the radical function, isn't it? It's kind of close. Why? Why is it close? I could rewrite this, couldn't I?
Yes.
I could rewrite this. I could say, let's see, let's make y the subject. So my next line would be plus or minus the square root. Okay, good, fine, that works. Okay. So in some ways, they're excited about circles. In some ways, this is kind of a special version of the radical function, okay? But it is, I think there is a difference. I think there's a crucial difference. Because the square root signs were introduced by us, right? We had to muck around with it, right? I think this is a little bit different. I would call these, now don't forget, I'm talking about, did I write it? I'm talking about domain restrictions, not range restrictions. They are related, but they're different, okay? I'm going to call this, and this is my last category, by the way, even powers of y. Right? And whenever you have an even power of y squared, y to the 4, y to the 512, right? You're going to have a restriction because it is related to this one. Okay? When you've got an even power, some things have to be positive. Now, better than turning this into a radical function, which is not really, right? It's a relation, so you can only approximate it with two radical functions. I would say this. I'm just going to leave it there, okay? And I would say, therefore, here the denominator can't be 0. Here, that thing has to be greater than or equal to 0. Here, that's got to be positive. What's going on here? This function, right? What's the smallest it could possibly be? 0, right? It's related to this. Yeah, they're flip sides. Can you see it? Right? So whatever this is, in this case 1 minus x squared, that's got to be greater than or equal to 0. Let's see what happens. What does this thing look like? 1 minus x squared, that's a parabola, like so. 1, what are the intercepts? Minus 1, 1. It's got to be greater than or equal to 0. These values, minus 1 to 1, which sure enough is the domain of the unit circle. Okay? This is a nice quick way of working out the domain. Now with a circle, you're like, I know what a circle looks like. I don't need to. But in a second, we're going to look at this guy. Okay? And working out the natural domain is not quite so easy because it's not a familiar shape.